Hi, today I'll be talking about acid and base equilibria. So as part of my introduction review, I'll be talking about buffer systems. So for buffer systems, contrary to popular belief, it is not the loading icon in your average YouTube video, but it is actually I would almost say thing that resists pH changes. And so it contains appreciable amounts of either a weak acid and its conjugate base, or the exact opposite being the weak base and its conjugate acid. And in terms of function, it has the ability to neutralize small quantities of a strong acid or base, so hence resisting that pH change that I talked about. And so there are two types of buffer systems, one being acid buffers, so this maintains the pH to be some value less than 7, versus base buffers, which maintains the pH at values greater than 7. And of course that intuitively makes sense, right? Less than 7 is acid, more than 7 is base. So when we talk about buffer systems and anything of the like, it's important that we discuss the Henderson-Hasselbalch equation, which is written over here. And I'll start by describing the right side, so this term of the equation. So this is essentially the concentration of the conjugate base over the concentration of the conjugate acid initial. So conjugate acids and bases are essentially acids and bases that differ by one proton, so denoted by an H+. And a conjugate acid is formed when a proton is added to a base. So if a conjugate acid would just be a proton, and then you're adding to a base. And then by the same token, a conjugate base would just be a proton being removed from an acid. So essentially you would have an acid and then minus your proton. Now the next term we have is pKa. So we've learned about Ka, which is the equilibrium constant, and this A here refers to an acid, but we can also change this to a pKb, which would just be the power of the equilibrium constant of a base. And essentially what the new P here represents is the how tightly a proton is held by a Bronsted acid or base. And essentially if we have a Ka value and we want to convert to pKa value, we can just think of P as negative log. So that means that pKa would just be negative log of the equilibrium constant of the acid. And of course, lastly, we have the pH. This we already know, power of hydrogen, pretty standard stuff. So while the Henderson-Hasselbalch equation seems to be able to be applied to lots of things, there are several conditions under which that have to be met in order to actually use this equation. So the first one is this term, the concentration of conjugate base over concentration of conjugate acid. And essentially, this has to be between the range of 0.1 and 10. And so essentially, the reason why we need such a condition is to meet the point that the buffer solution has to have appreciable amounts of the acid and base, essentially. And so another condition that is supposed to satisfy that same point about containing appreciable amounts is the concentration of the base and the acid. Both have to be a lot greater than the equilibrium constant, so shown by those arrows. And usually a good number to be larger by is by magnitude of 100. So essentially you want to have the concentration of the base and the acid to be at least 100 times larger than the Ka, compared to the Ka. So to really drive this Henderson-Hasselbalch equation home, I'm going to be using acetic acid as an example as an example problem to explain the Henderson-Hasselbalch equation, but I also want to explore the applications of acetic acid. So first, acetic acid was used in photographic film. Now, of course, this isn't very applicable to a whole lot of people anymore, as there are newer cinematography techniques, but it's very important to know that it used to be the primary source of a part of the photographic film. And then if we're moving a bit forward in time to today, acetic acid is also used in certain plastic production, and as we know, there is a lot of plastic in the world, so it's very significant. But of course, the most common thing that we know about acetic acid is that it's usually just called vinegar. Of course, vinegar we use a lot in cooking, and we have it, and I actually enjoy vinegar quite a bit myself. And the last point here is really drives the point home about how important acetic acid is, and that is that it is projected that there will be 21.66 million tons of acetic acid in the world by 2023. So just a large number to really show how important acetic acid is and how present it is in our current society. So here we have the example of acetic acid, and so here what we're given. So we have a pH of 4.91. We're also given the millimoles of acetic acid and a Ka of 1.7 times 10 to the negative 5. And we are trying to find the millimoles of the conjugate base, and I'll just say it's, I don't know, let's say sodium acetate. So the first thing we can look at is maybe the pH. We're given this in the question, so there's nothing too special here. And the next one is a pK, which is a little complicated, but really not that complicated. So we know that pKa equals to the negative log of the Ka. So therefore, that would just be the negative log of our Ka, which is 1.7 times 10 to the negative 5. I'll maybe fix up the period here. And that should give us around 4.75 as the pKa for acetic acid. And so we can sub that value into the Henderson-Hasselbalch equation. And then this last part is the log section. So we know that the millimole of the weak acid is 25. It's given to us in the question. So we're going to replace it in the weak acid section, and then we're going to have X, which represents the millimoles of conjugate base. So if we were to put everything together, we have 4.91 for our pH, we have 4.75 for our pK, and then we need to add the log term. So log X over 25. And so we would move the 4.75 over to the left side, so then it would become 0.16, and then equals log x to the 25, or x over 25. And so to cancel log, we simply move everything to the power of 10, so 10 to the power of 0.16 equals x over 25, because 10 to the power of log cancels. And so this just becomes a simple math question. 10 to the power of 0.16 is 1.44. And I'll just write the equal here to save some space. And so we have x, and then this, but we just move the 25 over, so we would just multiply 1.44 by 25. And therefore, our x equals to 36.135, and that is, of course, equal to millimoles of the conjugate base of, I think I said sodium acetate, right? Millimoles of sodium acetate. I'll just write it like that for now. And so that concludes the example for Henderson-Hasselbalch equation, and just shows that given certain parameters, we were able to find other parameters within the question using this Henderson-Hasselbalch buffer equation. So to end off this tutorial, I'd like to include an application of buffers that I think is pretty useful, and that is called gel electrophoresis. So it used to be used as a DNA sequencing technique. So we would find the DNA of an alleged criminal, and then we would put his or her DNA inside this machine, and then we would determine or match these patterns to any pre-existing DNA records and identify whether they are the criminal or not. So how does it work? Well, if we were to use a bit of electrochemistry, if we had to add another topic here, we have a negative side and a positive side. And so this is the side view and this is the bird's eye view. So we would have a cathode and we would have an anode. Now we would place the DNA on this side, the cathode side, and the DNA is actually negatively charged. So if we were to connect a circuit here, and we were to turn, let's say, a machine on, energy source on, then that means that the DNA will start moving towards the anode because of the positive-negative attract rule. And so when we look at the bird's eye view over here, we can see that the direction that the DNA is being pulled is downwards. And essentially, it's this pattern that varies between individuals. So let's say the bottom one that I just circled here is another person's, and we have the first person's, which is circled here, and they're different, that would just mean that there's no match. So we understand that, but how do buffers come in? Well, you might have noticed that there's this blue section here, and that is actually all buffer. So this entire thing is filled with buffer. Now, why can't we just use anything else? Well, the first thing is that the main goal of the buffer is to have some sort of floating solution so that the DNA can actually float across and move towards the anode. But also, the goal is also to maintain a neutral pH. So if neutral pH is not maintained, so let's say that we had an acidic solution inside the container instead. Well, we know that acids release protons or H+. And we also know that DNA is negatively charged. So positive negative attract, and therefore will mess the DNA up. And so basically this gel electrophoresis result is going to be completely skewed and it wouldn't work. So that's why buffers are such an integral part of gel electrophoresis. And really just goes so far to show that chemistry that we learn is really applicable to one of many ways that our society upholds law and order in this case, right? Because of forensic and criminal investigations. So in summary, today we've talked about many things about buffer systems, including their properties, the Henderson-Hasselbalch equation, and its applications in terms of acetic acid in buffers, as well as the application of gel electrophoresis in forensic science and the justice system. So all of these points I've talked about today really show not only how buffer systems work, but how important they are to us for our society to function in very specific areas.